All right, good day, everyone. So we did weight, ratio, and proportion in class. We did the introduction of it. And what we're going to do today is continue with the expansion of the ideas of what happens in terms of proportion. So recognizing that, and of course, understanding that this is a year 4 course, right, means that we need to build our skills that we got in the previous courses from last year's 3001 and the two before, in which we looked at all that pedagogy and understanding of the theory in terms of how to teach, how students learn as well, and we incorporate that within our topic. So, of course, we're going to continue where we look at the whole idea of the breakdown from the course outline, that in the ideas of weights, ratio, and proportion, that there are 4 major areas, and we have already done the first 2 parts. So we're now going to look at the conceptual and relational understanding of proportion, and specifically direct proportion. So when we think about that, let's look at a little example. Let's put up a little seesaw where we have the idea that right now we have 0 on the left and 0 on the right, so they are balanced. And if they're balanced, right, let's consider we're putting 3 of those blocks on the right-hand side, 3 heavy blocks, maybe concrete blocks. And clearly the seesaw goes down to the right. Therefore, the right side is greater than the left side in terms of mass. Let's now put a boy on the other side, and hopefully we'll see that they are balanced. What does that tell us? It gives us the idea that if we consider that they are equal distance apart, that one man or one boy weighs 3 blocks. So before it started that we had 0 men and 0 blocks, it was balanced. Now with 1 man, for it to be balanced, we need 3 blocks to balance it. Right? And we start to see some sort of relationship between one and the other. Let's continue. We had the idea that we know 1 man weighs 3 blocks. And if we develop on that, and what happens now if we have 6 blocks and we put 1 man? Will that be able to shift the weight and cause it to be level so it is balanced? More than likely, no. So it is not balanced at this point in time. Right? So what we say 1 man is not equal to 6 blocks in terms of weight. So how do we do that? Let's picture the same scenario again. And we have 2 men now. So with 2 men, it balances the 6 blocks. This tells us that 2 men weigh 6 blocks, and we could have our table. 0 men needed 0 blocks in order for it to be balanced. If we had 1 man, we needed 3 blocks for it to be balanced. And if we have 2 men, we need 6 blocks for it to be balanced. And hopefully we could see a pattern there. So it could tell us that we could take that information and extrapolate it even further. That if we have 3 men, it should take 9 blocks to balance. So we could see that we're having some sort of ratio. So as the men amount, meaning the number of men increase in order for it to be balanced, then the number of blocks has to increase. So if we try to sketch a little graph from here to give us an idea what's happening, we started with the x-axis representing men, 0, 1, 2, 3, and then we can extrapolate and see from this idea what happens if we have 10 men. How many blocks do we need? Or 100 men. And if men are on one side, what do we need on the other side? We need blocks. So, recognizing this, a little graph from our information that we had 0 men, 0 blocks. With 1 man, we needed 3 blocks. With 2 men, for it to be balanced, 6 blocks. With 3 men, you needed 9 blocks. And therefore, with 4 men, it should take twice the amount as 2 men. So it should be 12 blocks. So we see this is a straight line graph. And because it's passing through the origin 0, 0, where the two axes intersect, we can say that this is what is considered to be a directly proportional graph. Simply speaking, as the men increase, the number of blocks in order to balance it will increase. And it starts from the idea of passing through the origin, the intersection. However, if we had a straight line graph where it was a little higher, and this is something we would have seen in Form 4 and 5 in secondary school, we would say that's a straight line graph, which is both of them are straight line. And we would describe the purple line as being linear. And this orange line is also linear, but it's specifically, we can say it's directly proportional because it's passing through the origin. And if we compare the ratios, when we had 1 man, we required 3 blocks. And when we had 2 men, it required 6 blocks. And as such, 3 men requires 9 blocks. So we were saying before that the idea of proportion really can be represented as equivalent ratios, that 1 to 3, in terms of men to blocks comparison, is the same as 2 to 6, which is the same as 3 to 9. So let's go on. Let's look at the idea of proportional. This is a statement expressing the equality of two ratios, just repeating what we just said. Two variables are related by a fixed ratio. In our case, the two variables were men, the number of men were varying with regard to the number of blocks. So when one variable increases, as the other increases. So we consider that to be directly proportional. As X increases, Y increases. As men increases, then the number of blocks increases in order to balance it. So let's look at an example. Right? We have the same scenario there. In the first case, the number of men, in the first case, compared to the number of blocks, that was 1 to 3, is the same as the second case, number of men, to the second case of number of blocks. So we can see these scenarios where we're showing that they're equivalent. How can this also be described? It can be described as saying men would be some number for this particular example, some factor which is constant. So men times some constant will give us the number of blocks. And recognizing that, we can simplify it and look at it differently by saying, well, as we think about the number of men increases, this implies or this tells us that the number of blocks increases. So the symbol for directly proportional looks almost like an infinity sign. So it tells us that men are directly proportional to blocks. So that's the mathematical way of seeing it. Let's look at another couple of examples. If we consider for a circle, the area of a circle is pi r squared, and we know pi is 22/7, normally described as that value, 3.142 and so forth. Pi is considered to be a constant. So if we're comparing the area to r squared, then area is equal to some constant, which in this case is pi, times r squared. So it gives the same idea as in men with the blocks, that relationship. So it means that we can say as the area increases, then not r, but r squared increases. And we'll do an example coming up showing that. Or it can simply be written as A is proportional to r squared. And r, now one more example. We did a linear one, a quadratic one. Let's do a cubic one. The volume of a sphere is 4/3 times pi times r cubed. So 4/3 will not change, and pi will not change, 22/7. As such, 4/3 times pi is a constant. Therefore, we can say the volume is equal to some constant times r cubed. Not r, but r cubed. As such, we can say that when we consider the volume increasing, that means r cubed is increasing the same amount. Or we can say in mathematical terms, volume is proportional, directly proportional to r cubed. So now let's look at an example a little further on. Considering the pressure law, for some of us that had done sciences at secondary school level, right? So pressure of an ideal gas at a constant volume is directly proportional to the absolute temperature. So we're saying pressure is directly proportional to the absolute temperature. And if we get these values here, knowing that is the case, that they're directly proportional, we're relating pressure to temperature just as we related men to blocks, then we can do it a couple different ways. Let's give an example, because we're thinking of it conceptually, meaning we have to see or formulate some sort of image to represent what's happening. Well, if we think about it as a graph, pressure versus temperature, we know if it is directly proportional, it must be passing through the origin, right? And let's put up the axes as well, right? Temperature and pressure. Then we know it's passing through the origin, and we also know when the pressure is 1000, which is on the y-axis, the temperature is 400. So we know 2 points. And if we know 2 points, 0, 0 always, as we say, directly proportional must pass through there, and 1000 for pressure on the y, and 400 for temperature there. And if we know 2 points, what do we know about a directly proportional graph? It is a straight line. Since it's a straight line going on infinitely, then can we figure out what happens when the pressure is 800? Could we figure out the temperature? Well, we could start at 800 as the pressure, go across, and wherever it hits, at that point, that will give us T1, temperature when the pressure is 800. And that works out to be, if we were plotting this graph accurately, 320. What happens so we found T1, how do we find P2? Since it's still directly proportional, what do we know? We know the temperature is 600. So if we look on the x-axis where the temperature is 600, we can draw a dotted line up, and wherever it hits that blue line, or directly proportional representation, then we can go across to the left, and we can read off, if we plotted it correctly or precisely, exactly what the pressure will be when the temperature is 600. So P2 is 1500. All right, so we did another example there. We did the man and the blocks balance. We did the pressure law. Let's see if we do one more example on directly proportional. So let's consider the same example, but solving it purely abstractly. So remember that a straight line graph represents a directly proportional graph. Y is equal to mx plus c. C is the point where it's cutting the y-axis. Where does the line meet the y-axis? At 0. So C is 0, so we don't have to write it. We can just write y is equal to mx. And in this case, the y-axis, if you remember just now, the y-axis was pressure, and the x-axis was temperature. So we can write it as pressure is equal to some constant multiplied by temperature. So let's look at our values again, and let's see if we can solve it abstractly now rather than graphically. So we try to do it in a conceptual way first by showing us what it looks like, right? So we can see an image, and now we can go through the algorithm, right? The normal abstract way, right? So it's up to you which choices there are. So now, what do we know? We know we have an equation with the ideas of 3 items in it. Pressure is equal to some constant by temperature, P, K, and T. 3 terms. If we look at our table, in the middle, line of information, we know the pressure and we know the temperature. So if we know P and T, and there are three terms in there, then there's only one term that is missing. And that missing term is K, the constant. Now, K is normally what you use for constants, or C differently. So if we put in those values, 1000 is equal to the constant, whatever it is, multiplied by 400. Can we find for K now? From the ideas of mathematics, as long as there's only one term that's missing on the line, we should be able to solve it. So if we think about the idea that we only want K on the right side, we have to remove that 400. So what we do is we divide by 400 on the right side and divide by 400 on the left side. So if we divide by 400 on both sides, then we get 1000 over 400 is equal to K times 400 over 400. And that will give us 400 over 400 is 1, so it'll give us 1K. So now 400 into 1000 is 2.5. So now we know the constant for this particular question. As such, if we had to rewrite the equation now for this particular situation, pressure is equal to the ideas of what is the constant? 2.5. So pressure is 2.5 T. And if we look at the first line now, so pressure is equal to 2.5 T. There are two values there, P and T, which we do not know. If we look at the first line, we know P and we don't know T. So if we know P and we know 2.5, there's only one thing missing. So let's substitute. 800 is equal to 2.5 times T1. So there's only one item missing in the equation, so we are supposed to be able to solve it. The 2.5 is multiplying on the right-hand side. So if we want T1 alone, some teachers will say, well, carry the 2.5 across and divide. What it actually is happening is we're dividing by 2.5 on both sides. Just like the seesaw, we want to maintain balance. For students to understand balance at the levels in schools is to recognize whatever I'm doing on one side, I must do on the other in order to maintain balance. So if I divide by 2.5 on the right side, then the 2.5s will cancel and it's left with T1. And I divide by 2.5 on the left side, so it'll be 800 over 2.5 is equal to T1. And that works out to be exactly 320 T1, which is the same value we got when we looked at the graphical method. And finally, we want to look at the last part where we have the same formula, pressure is equal to 2.5 times T, and we want to find P2. We know 2.5 and we know the particular temperature at that point is 600. So if we plug that in, we see P2 is 2.5 times 600. As such, we could solve for there, use our calculators. So 2 by 6 is 1200 and half of 600 is 300, 12 and 3 is 1500. So the pressure P2 is 1500, and these are the same values we got. We did it graphically, and we've done it in an algorithm sort of format. So let's do a third example now. We did the man and the blocks, we did the pressure law, and we're going to do the force using as a third example. So because it's directly proportional, y is equal to mx and plus c, and the c is 0. And for this particular question, the force is equal to kv squared. That's the force of resistance when you're jumping out of a plane, or the air resistance that's holding you back. So let's look at the information. Now we can solve this by plotting a graph, doing the same thing, 0, 0, and 75, 2.5, those 2 points. Draw a straight line and read off from the graph. In this point here, I'm going to show you how to do it using our algorithmic method. So F is equal to kv squared. There are three unknowns, F, K, and V. But if we look at the top line, we have F and V. So if I substitute for F and V, then the only thing we'll be missing is K. So I can write that force is equal to 75, which is equal to K, the constant, times 2.5 squared. Do not forget the squared. Right? And what we can do now, if you want, there are different ways to do it. We can just expand the 2.5. 2.5 times 2.5 is 6.25. And if we want to find K, We divide by 6.25 on the left side and on the right side. On the right side, they will cancel out and be left with K. On the left side, it'll be 75 divided by 6.25. So K works out to be 12. So the constant for this particular situation is 12, which means if I'm rewriting the equation, I will be writing F is equal to 12 V squared. So if we look at the second line now, we want to find M, which is for the particular force, and we know V, velocity, is 4. So if we substitute in there, then M is equal to 12 times 4 squared. 4 4s are 16. So 12 times 16 is equal to 192. So we know the force is 192 when the velocity is 4. If you're plotting a graph with force on the y-axis and velocity squared on the x-axis, you will get a straight line whose gradient is the constant 12. Let's now go look at it for the last one. F is equal to 12 v squared. And in our last piece of information, we know F, 2880, is 12. And v velocity is represented as n squared in this particular case. So we want to find it. We can divide by 12 on both sides. We're going to get 2880 over 12 is equal to 12 over 12, which is just 1 n squared. And 12 into 2880 is 240. So 240 is n squared. That's not our answer. We want to find n. So n is the square root of 240, which works out to be approximately 15.5. So we have done multiple examples of those. Let's now move on, because we looked at setting up the ideas of directly proportional, looking at it graphically, looked at the example with man versus blocks, and of course we looked at force versus v squared, and pressure versus temperature. Now there are some exercises here. There are 4 questions that you can practice. So you can pause the video now, go and solve for them. In each case, they're directly proportional. Number 1, given that y is directly proportional to x, so we can write y is equal to kx, and go through the format, or you can plot your graph and solve for A and for B. In part 2, P is directly proportional to Q squared, so P is equal to K Q squared, and then do the same format. Or if you want to use another constant as M or B, because K is in the question, that's okay. In number 3, A is directly proportional to B cubed, so A is equal to some constant times B cubed, and solve. And finally, Y is directly proportional to the root of X. So Y is equal to some constant times square root X. And we can solve. So now I'm going to show you the answers. So if you work them out, I'm not going to go through them, but the solutions are the following, right? Where we found for each of the unknowns: 45 and 88, 24.5 and 9, 64 and 0.1, and of course, 64 and 60. So that's given us an idea of what this directly proportional could look like, right? The ideas of equivalent fractions. Let's think of the idea of connecting it to what we did in fractions a couple courses ago and last course. That if we look at the situation, we have a whole, and we cut it up into 4 parts, and we look at what is shaded, that is 1/4, and trying to relate it to other topics. If I draw a line across, is the shaded area changing? It has not. But the whole is now cut up into 8 parts. So how many parts are shaded? 2 out of 8. It's the same green shading as 1 out of 4. So 1 out of 4 is the same as 2 out of 8. Let's remove that line. So we can still see 1 out of 4. What about if we send 2 lines across? Then what happens is the green shaded region still remains the same, but now how many parts do we have? We have 4 by 4 and 4. That's 4 threes are 12 parts. And how many parts are shaded? 3 out of 12. So it shows you ratio 1 out of 4 is the same as 3 out of 12. Just like when we did the proportional relationship between man and blocks, 1 out of 3 was 2 out of 6, 3 out of 9, and so forth. So we move it again. We still have 1 out of 4. It hasn't changed. And what about we send 3 lines across? Then we're going to get 4 parts by 4 parts, 16 parts. So how many parts are shaded? 4 out of 16. So 1 out of 4 is the same as 2 out of 8, or 3 out of 12, or 4 out of 16. The 1 out of 4 is still there. Let's do one more like that. And let's send 4 lines across. So we cut it into 5 parts going up and 4 parts across. So that's 20 parts. How many parts are shaded? 5 out of 20. So we've seen 1 out of 4. And now we can say a quarter is equal to 2/8. If we're thinking of fractions in terms of proportional, we're just relating 1 out of 4 to 2 out of 8 to 3 out of 12 and so forth. And this is similar to our multiplication tables. If we look at our 1 times table, 1 ones are 1, 1 2 is 2, 1 3 is 3, 1 4 is 4, 1 5 is 5. What about our 4 times table? 4 ones are 4, 4 twos are 8, 4 threes are 12, 4 fours are 16, 4 fives are 20, which we know. And look, you could see your equivalent ratios there. That 1 over 4, a quarter, is equal to 2/8, which is the same as 3 to 12, or 4 to 16, or 5 to 20. Let's now look at another example. So let's cut it up again. And we're going to cut it up and shade 3 parts this time. 1 quarter, 2 quarters, 3 quarters. So we could say we've shaded 3 quarters. And if I put a line across, such as we did before, it's the same shaded region, it's the same 3 quarter, but how many parts are now shaded? 6 parts out of 8. So we can see the equivalence of these ratios. 3 over 4 should be the same as 6 out of 8. If we remove it, we still see 3 out of 4. And we could put it back in with 2 lines now coming across. So we have 4 threes are 12 parts. How many parts are shaded? 9 out of 12. If we remove it, we still see 3 out of 4 shaded. And if we draw the lines across, we're going to see 4 fours are 16 parts in all. And how many parts are shaded? 12 out of 16. So 3 over 4, or 3 to 4, right? We could think about this as a part to whole relationship. At 12 of the parts are shaded out of the whole thing, which is 16. Or we could say 3 of the parts are shaded out of the whole, which is 4 parts. Then split it up again. So we have 4 5s are 20 parts in all. That's our whole. And our part that's shaded is 5 3s are 15. So 15 out of 20. That means we can see if we have our 3 times table in there, then 3 ones are 3, 3 twos are 6, 3 threes are 9, 3 fours are 12, 3 fives are 15. And the same ratio 3 to 4 is the same as 6 to 8, or 9 to 12, or 12 to 16, or 15 to 20. So a little integrating of this ideas of proportion into other topics that we've done already. And we've done that same thing, and there's another method in which we can find the equivalent ratios. That if we have 1 to 2, and we want to say, well, what is that compared to something to 10? Right? So how do we go? There are different ways to do it. We could say 2 times what will give me 10? 2 times 5. And just like a seesaw, and maintaining that balance because there's an equal sign. Then if we got 5 times the amount, then we need to have 5 times the amount on top as well. So if we're saying that for every 1 man, or for every 1 boy in class, there are 2 girls, and we maintain that ratio, by the time there are 5 boys, it means there are 10 girls. So what we do below, we do on top in order to maintain that ratio. Let's try another one. Let's say 2 to 3. And we say that below, it's going to 12. Then 3 times 4 is 12. And if we multiply by 4 on one side or below, then we need to do that above as well. So that's going to give us 8 to 12. So the ratio 2 to 3 is the same as 8 to 12. And this is integrated in other topics as well. And so let's remind ourselves, just as what we spoke about just now. We had 1 to 2. That's the same as 5 to 10. Or sine 30, because if we integrated it, that is the ideas of what trigonometry is. Trigonometric ratios gives us the ratio, the comparison of the opposite to the hypotenuse if we're talking sine, or if we're talking cosine, then it's adjacent hypotenuse, and that will still maintain that ratio. If the angle is 30 degrees, sine of that 30 degrees means the ratio when it's 30 degrees of the opposite So the hypotenuse is 1 to 2. Or if you make the triangle a little bigger, 2 to 4. Or even bigger, 5 to 10. Or 7 to 14, because it's maintaining that idea for ratios. So we've done the concept of and the relational understanding of directly proportional. We've looked at it in terms of graphical representation, algorithmic representations, and we've sort of integrated it and connected to other topics in math as well. So now, let's be reminded of the 2/3, that we have the ideas of 2 to 3. That's ratio is maintained with 8 to 12. So now let's move on from directly proportional into the final aspect of this topic, in which we're looking at, in this content area, conceptual and relational understanding of proportion, but the indirect relationship, not the directly proportional, the indirectly proportional. So we're going to look at that area here, last one, in order to complete the topic. So what happens between direct and indirect? Well, let's look at the definition. Proportional is a statement expressing the equality of two ratios, as we said before. Right? Two variables are related by a fixed ratio. We've also said that, so we have that constant multiplying by it. However, when one variable decreases as the other increases, so one is getting bigger, the other is getting smaller, then that is known to be indirectly proportional. So we could think of it many ways. One simple example would be if we had 6 persons sharing up all the work to sweep the classroom, it will take a certain time. If we had less persons, let's say it took 10 minutes. For 6 persons to sweep the classroom, it took them 10 minutes. If we cut that 6 persons down to 3 persons, so the number of persons, in that case X, is going down, do you think the time it will take to sweep the classroom will go down or go up? It will go up. It will do the opposite things. So when they're moving in opposite directions, as one goes down, the other goes up, or one decreases, the other increases, that is indirectly proportional. So let's look at an example, right? We looked at the ideas before, the pressure law. Now let's look at the Boyle's law. Pressure of an ideal gas is indirectly proportional to the volume. And we're going to go through a couple of these examples in order to set up what the graph looks like. So if we picture, we have a container, right, with 3 boys standing on it, pressing down on this gas, then you could see that for 3 boys, it's a height of 2 blocks on the right side, 2 yellow blocks. Right? So we're getting that general idea. Boys, 3 boys, what's the height? 2 blocks. And now what happens if we remove 1 block? We're holding the piston right there, and remove another, right? And as we let go of that piston now, will the air remain the same amount? Is it the same weight pressing down, squeezing down that blue gas in there? It's less now. See, there's only 1 boy now. What do you think is going to happen to the height? Is it going to remain the same? Is it going to come down because there's less boys, or go up? Well, it's going to go upwards. And it's going to go upwards 1, 2, 3, 4, 5, 6 blocks. So when we had 3 boys, the height was 2 blocks. That was being squeezed, compressed. When it's only 1 boy, the gas will be able to expand because there's not so much weight on it. And as such, then there's going to be a difference in the height being increased. That one decreases, the other increases. So we try to plot that, and we look at the ideas of going across and seeing number of boys on the x-axis versus the height on the y-axis. Let's plot the first one, where we had 3 boys. The height was 2 blocks. Hope you can see the height being the blocks in blue and yellow on the right-hand side climbing up. And when there's 1 boy, the height was 6. As such, does this graph look like it's going through the origin 0, 0? No, it's not. And instead of going up to the right, it's actually coming down. It's doing quite the opposite. So let's go on. let's look at the idea now. We have that information. We started with 3 boys with a height of 2. Now we have 1 boy. The class expand to a height of 6. So now let's add some boys. 1, we're holding the piston right here, and we're just adding weight. 2, 3 more, 4 more, 5 more. So in total, there's 5, and there's 1 boy there. There's a total of 6 boys. We're holding that piece that they're standing on tightly there, and it's waiting. And now, what that means is we have 6 boys. What's going on with the height? It will squeeze it down even more than ever before. So much so that it will now reach a block of only 1 height. So when it was 3 boys, the height was 2. Now it's 6 boys, it's twice the number of boys, the height cut in half to 1. If we try to repeat it and show it graphically what's happening, then as we set up the ideas of the x-axis being boys and the y-axis being height in terms of blocks, we had 3 boys, height of 2, 1 boy with a height of 6, and now 6 boys with a height of 1. So if we connect it, you can clearly see it's a curve that's happening. And that curve obviously is not passing through the origin. Let's go on and carry it one step further. So we have that situation in there. And now what we're going to do, we're going to think about it if there were only 2 boys. If there were 2 boys, will it be as much people increasing or decreasing, pressing down? Well, if there are only 2 boys, we would remove some boys from there. Let's hold it for a little while. Remove 1, 2, 3, 4 boys. If we remove 4 boys, look what's happening. The gas will be able to expand. The height will increase. Right? So with 2 boys, the height goes up to, let's count the blocks there. 1, 2, 3. Now, if we have our similar ideas of setting up the axes, and we're bringing in all these points, 3, 2, 1, 6, 6, 1, and of course 2 boys, 3, then you can see a smoother curve is happening. And the more we do, more accurately you'll get this nice smooth curve starting from very high up, close to the axis, and curving down till it gets very flat. But that's the idea of indirectly proportional. So if you have an accurate curve, then you can read off all the values for any questions that were tested from like what we did before with the straight line. So let's remember that when we think about it numerically, right, not graphically, that for that situation, what we recognize, let's look at the numbers. We have 3 boys, a height of 2. What about that 3 and 2? We had 1 boy and a height of 6. Can you see anything close with the 3 and the 2? And the 1 and the 6? If we had 6 boys, we had a height of 1. So look at the pairs, 3, 2, 1, 6, 6, 1. And with boys of 2, the height was 3. So can we find anything with those pairs? Well, each one of those numbers, 3 twos are, what did you say? 3 twos are 6. 1 6 is 6. 6 ones are 6. 2 threes are 6. So the 6 is the constant. What that means is if we take the boys and we multiply by the height, it's given us a constant, which in this case is 6. So we could say it a little differently. We can say boys will be the constant divided by height. So you see how it's a little different from directly proportional? Directly proportional, we'd say it would be constant multiplied by it. Here it's constant divided by it. So that is telling us that as the number of boys increases, the height decreases. So it's indirectly proportional. That's what we're trying to explain. Or how do we see that mathematically? The boys are, and the symbol for proportional is that red sign in the middle that looks like an infinity almost. And indirect is 1 over height. So other examples, let's use the idea of the gravitational force of attraction, where F is equal to gmm on r squared, and gmm is a constant, then it's some constant divided by r squared. So what that means, the force of attraction, let's say between the Earth and the moon, will be proportional to the r squared. So as the force increases, R squared decreases. Or we can write it F is indirectly proportional to 1 over R squared. Let's look at this one here with a square root in it. So 2 is a constant, pi is a constant, right? And m is a constant, the mass. So this is for a pendulum swinging like a grandfather clock, right? So what it means is some constant divided by that. As such, as the temperature, as time goes up, that comes down, or 1 over it. Gives you the same idea for square roots. And those are some formulas done in physics. We did some examples in chemistry, trying to link it to other areas as well, because some of you have experienced those things. So let's go look at an example now. And we're going to use the same idea of the Boyle's law. Instead of doing it graphically, we're just going to do it algorithmically because the graph needs to be really accurate. So when we're writing our formula, it's not mx, it's our constant over x. So the relationship with Boyle's law, pressure is indirectly proportional to temperature. So pressure is equal to K over T instead of K multiplied by T. That's the difference between directly and indirectly. Let's bring up this question here. And if P is equal to K over T, we have 3 variables, P, K, and T. And if we look at our table, you can see in the second line, we have pressure and temperature. So if we know P and T, we can put it in there. Let's substitute, right? Because that's what we're looking at specifically to help us get our K first, and then we could go solve the others. Because if we tried working on one of the other lines, we'd have 2 unknowns. So we have pressure is equal to 1,000 K over 400. So 1,000 times 400 is equal to K. Therefore, K is equal to 400,000. And then, if we found K, now we rewrite our formula. Pressure is equal to K, 400,000 over T. Then, think about the first line. What can we do? We know pressure. And we want to find temperature. So 800 is 400 because we know P, 400,000 divided by T1. So the T1 is dividing, we could carry it across. So it'll be 800 times T1 is 400,000. If I want to find T1 alone, we could divide by 800 on both sides. 800 means that we're going to get 400,000 over 800. The 2 zeros cancel by 2 zeros, 8 into 4,000 is 500. So the temperature is 500. And let's try one more. We have the general formula, P is equal to K on T, but we know K is 400,000. So P on T, and if we look at our last line, we want to find P2. 400,000 over the temperature at that point is 600. And if we do some divisions, we're going to get 667. This gives us an example here of indirectly proportional. Let's do one more example. We're almost finished. One more example here, where we're looking at the ideas of it being a formula where we have R squared involved. So K is our constant. Let's look at same values again. So we know which one can we look at first. Is it the bottom line? We will not know the value for the force. It will be S, and we don't know K. So we can't use the bottom line. Can we use the middle line, 125 and R? Well, we know F, but we don't know R, and we don't know K. There are still 2 unknowns, and there's only 1 equation. So generally, in our math understanding, if we have 2 unknowns in 1 line, 1 equation, we can't solve. We need only 1 unknown for 1 equation. If there were 2 unknowns, we needed 2 equations, and we'd solve that simultaneously. So we'd have to pick the top line because we know F and we know R. So if we know F and we know R, we could find out for K. K is the only unknown. So let's substitute. 4,500 is equal to K over R squared. Don't forget the square. So R squared is 9. The 9 is divided. I can carry it across. 4,500 times 9, which is 40,500. That is our K for this particular question. So if we rewrite the formula, we wouldn't be writing F is equal to K on R squared. We know K. We figured that out. In some questions, you will find that they ask you to find out what is the constant of proportionality, meaning what is K. before you have to go and find those. So if you're doing it algorithmically, then it's a good practice to go find k first. There are other ways to solve it. There are always other ways. We could have written 4,500 over 3 is equal to 125 over r. And then do a relationship. Sorry, 4,500 over 3 squared is equal to 125 over r squared, and do it like that. But it's a good practice to find k as a constant first. So f is equal to 40,500, which we just worked out, over r squared. And in the second line, we know f is 125. So 125 is equal to 40,500 over r squared. And the r squared is dividing. When I carry it across, it will multiply. So 125 times r squared is equal to 40,500. If I want r squared, then I just divide, carry it across. So r squared works out to be 324. So what is r? R is square root of 324, which is 18. So we found r. Let's try our last line now. We know our formula again, 40,000 over 500. All right, 40,500 is key for this question. And we substitute in the value for f is s and r is 6 squared. So 40,500 over 6 squared is 40,500 over 36, which works out to be 1,125. So we've explained the definition of proportionality, and in terms of direct and indirect, what we've done now is we've shown the explanation of what indirect proportionality is, showed it in terms of conceptually that you have an idea that when one goes up, the other goes down. We did it in terms of men and compressing the gas, right? And we're able to get a conceptual vision because the graph shows a certain way, so we have a general idea what it looks like, right? And now we did examples, the one prior to this, which talked about the Boyle's law, and now this one here in terms of r squared. So I'm going to give you 4 questions here that you can practice, right? Just as we did in directly proportional, we're going to look at it in terms of indirectly proportional. So given that m is indirectly proportional to n, which means if m is equal to k over n, not multiplied by n, right? Multiplied by n is direct. Indirect is k over n. Then, given that situation, can we find A and B? And how did we do it just now? We can take the pair that we know, the m and n, 70 and 10, and find out for the constant of proportionality, and then substitute it into there, and solve for A and B. We can do the same for the second one, which is y is inversely proportional or indirectly proportional. They both mean the same thing, to x squared. So y is equal to k over x squared, and you can go across and solve for this as well. Starting with the middle line in order to help us so we could find k. The third question, y is indirectly proportional to q cubed. So p is equal to k over q cubed. And we can do the substitutions here and solve. And finally, a is indirectly proportional to the root of b. So that means we're going to get some versions of that there. And of course, now these are your answers. So you can, after you pause it and worked it out, these are your answers to go there. And that brings us to the end of directly and indirectly proportional. So, people, thank you very much. Go through it and make sure you can work out your questions. And if you have any issues, contact me. Take care. Bye-bye.